Hey, Andrew McLaren here. So I wanted to make this video about if forming or releasing bonds, if they give energy off or if they require energy put in, mostly because there's this point of confusion that comes from when you're thinking about ATP and breaking that apart. It's a really common misconception. Even my AP biology teacher, when I was a student, had this as a misconception, and he went to, I think it was UC Berkeley. So a very smart guy, but it's really common. A lot of biologists think that energy is released the opposite of how it is in reality with chemicals and their bonds and their energies. So we want to kind of clarify what's going on in that situation. We're going to basically go over the main idea, like how does this concept work in general, and also a little bit in the context of ATP. And then we'll go over why ATP is really going to be, when you break that down, why that gives off energy. And we'll talk about resonance, some electrostatic repulsion, and some stuff with concentrations. And then we're going to look at some example problems. And this is more around the main idea of releasing energy and gaining energy and how that relates to bond energies and the energy of like a whole reaction. Because there's a lot of times you'll see this type of question on like the AP test. So this is an AP question. You can see they give you like bond energies and like the energy of the reaction. So you have to be able to work with that stuff a lot of the time. And I wanted to connect that also, that math with this concept. So the main idea when we're talking about bonds is that when you break a bond that needs energy, so energy is going to come into the system. And remember, plus signs, that shows something coming into the system. So that's really important that you understand that for chemistry, that this means to like enter. And that when we have the minus sign, this is to, or sorry, this is to exit, like energy is exiting the system. And then this is for when energy is entering the system. So when you break a bond, energy needs to enter the system. And when you form a bond, energy is released. This seems counterintuitive to people because people think, oh, you need to use energy to build things like in the real world, like building a bridge. But it's more like these things fall towards each other. Remember, chemicals, they want to form bonds. When we're saying they want, that means that they're more stable once they've formed those bonds. And chemicals are more stable when they've released energy. They're at a lower energy state. So when we are talking about like carbon and oxygen, when they form like carbon dioxide, they're at a lower energy state. And to do that, to turn it into a chemical like that, that's going to release energy. So it's kind of weird because when you form a bond, it releases energy. And you can think about the same thing when you have like H2 or bromine, like dimerized, or like fluorine or chlorine. All of those as gases, they kind of pair up with themselves. And it's because that releases energy. To do that, that releases enough energy for them to pair up with each other. And it satisfies their octet rules, their electron shells, right? So if you think about these things as like magnets falling towards each other, that's usually why, how I like to think of these things, and why they're releasing energy when they've bonded. And you can think of like a positive and negative charge falling towards each other, and that's going to release some sort of energy in the system. And you can think about vice versa. If you had two chemicals that are bound to each other, like a positive and negatively charged thing, even if it's only partially charged, they're still charged. To separate those two charges, you're going to need to put energy in there. So if you think about pulling apart two magnets, you have to put energy into that system, right? But magnets, they'll also fall towards each other freely and easily and use their own energy. You can actually even use that energy to knock other things around or add energy to other things. So there's a number of ways to think about this. Also, it's kind of like a ball on a hill falling towards Earth. It's kind of like those two objects falling towards each other. That releases energy. Or if you were to push a ball up a hill, that requires energy being put in. You've probably heard that ball on the hill model. I also sometimes like to think about these things as like satellites, like the moon going around the Earth, or like, like SpaceX, one of their satellites going around the Earth. And if you were to, have the satellite like fall closer to the Earth, it should get going faster. And so it's like that energy is getting released. It's also going to warm things up. That's it could fall towards the Earth freely and on its own and release energy. To get the satellite to be further away, that's not going to happen just spontaneously. You need to add energy into that system. So you might need to like fire a rocket or something to get it to go further away, if it's in a stable orbit, that is. So the question is like, well, what's going on with ATP? I thought ATP stores energy in its bond, and it's not really about just the ATP's bond. It actually has to do with there's all these other bonds that are going on. Because yes, you're making ATP turn into like ADP or AMP, but you're also, as you can see, kind of getting rid of some water here, and you're making this inorganic phosphate. And so to really understand what's going on here is, yes, you're breaking some bonds, but you're also forming some other bonds. And the specific energy of the bonds in this reaction ends up coming out so that you end up releasing energy. So like you can think of the products as being very, very stable. Like these things are much lower in terms of their energy. And so you're going to have a lot of energy released when you have stable products that are being formed. So it isn't really so much about does this release energy or not. It's more about like the size of the energy of the products being formed versus the reactants being formed. Because you can see these reactants, they're not very stable. These products, they're much more stable. So if you look at the change in energy, this is Gibbs free energy that we've got for this section right here. But it's very closely related to enthalpy. If you haven't seen Gibbs free energy, it's very, very similar. It's measured in joules and whatnot. It's energy. So it can go down in that energy, and it just means that the energy in the bonds here has released a lot more energy than in these bonds here compared to if there were no bonds at all. And so you can actually look at the amount of energy it takes to form these compounds, and you can actually prove this mathematically. You can look at how much energy they're releasing. And I did a little bit of math here. You can see that this is the amount of energy it takes to form the reactants. This is the amount of energy it takes to form the products. I got that from this table here. And you can see that the products here, a little bit more negative than the reactants. So to go from the reactants to the products, that final minus the initial, it's a slightly negative change. It goes down slightly. So you can think about this as it goes down slightly. It was like that negative number. This is the other negative number, but it went down slightly to go down to the products. And so you can think about it as like, okay, this is the amount of energy that we had in the reactants. This is the amount of energy that we had in the products in terms of how much they're released when those things form, right? And then you can compare the difference between the two heights, and you can see like, oh, that's the negative 36.06 right there. So you can see that is this difference right here, and it's going down. Also important to note, because it's exothermic, right? ATP, when that gets broken, it's releasing energy, but it's not so much about the ATP getting broken. It actually has to do more with like these other concepts of what's going on in the molecule that we'll look at in the next section. I just wanted to also show you can do the same kind of math idea with the other reactions, like the ADP forming AMP. It does go down slightly lower. So if you were to look at these chemicals, it is going to have products that are a little bit more stable than reactants. So it is spontaneously going forward. It is, giving off the energy. It's just not like, you can kind of see how they relate to each other. Like the products are more stable, and so you're going to have a release in energy. It has more to do with the total energy in the molecules than like, oh, did I break the bond in ATP? Because you're also breaking other bonds and forming other bonds. Okay. Next bit should help explain a little bit more about the complicated parts of ATP. Okay, so we're going to go over just like the main idea. We know that when you are breaking bonds, that's going to require energy being put in, and then when you form bonds, they're going to be releasing energy, so that's energy leaving the system. So you can think about kind of an oversimplified version of what's going on here is that the bonds formed have a larger value to them than the bonds broken. So the negative numbers are pretty large. The positive numbers are kind of small. So the net effect is negative, although the negative is due to the bonds that are being formed. If you look here, there's a new oxygen and hydrogen bond that's being formed here, and a new oxygen and phosphate or the phosphorus atom here bonding in there. So there's new bonds that are happening because you can see that this is kind of like coming in and attaching to the phosphate. So I believe that this oxygen is this guy right here. This hydrogen is that right there. And then there was a positive hydrogen, which ended up bonding to the negative oxygen that was like right there. So you can think about that as kind of an oversimplification of what's happening. This is kind of like the simple version. In general, the bonds that are being formed are going to release a large amount of energy. The molecules are going to be very stable that you form. And relative to the kind of unstable molecules here, they needed a little bit of energy plugged in to break their bonds, but not much because they're kind of unstable. So that's the main idea, is that, and also these are not the actual numbers. I just made some simple numbers showing that these are a number. And if you were to do the math, that the net change is negative 80 joules in this example. It's kind of hard to get actual numbers because, again, this is not really what's going on. This is just an oversimplification of the math. What really actually ends up happening is that we have some stuff going on with resonance. But the main idea is that there's a net negative change. That is important. There's like a more energy that's being released by what you've formed than the energy required to break what you had, right? So really what ends up happening is this potassium is very, very stable. If you look here, the potassium, that's a lot of energy released, especially for the number of bonds that it has. So the question is, why is potassium so stable? The inorganic phosphate group, which is sometimes written as Pi right here, that represents this phosphate group. So the really interesting thing is that resonance, this is something that you'll hear about more in like organic chemistry. I'm not going to go into a ton here, but the main idea is that the electrons get kind of shared. So when you have these double bonds here, you can think about this guy being pretty stable. If you move these electrons up there, that's less stable. If you were to like move these electrons both here, that's very, very stable, very unstable, right? So you want to have like charge that's kind of evenly distributed. You've probably heard that when you've learned about formal charge. So what ends up happening is that the electrons, these double bonds, kind of get shared between all four of the oxygens. And you can kind of see how some of these double bonds can kind of pop up and these other electrons can pop down. And they're kind of all being shared equally. And the double bonds can be on any four of them. And so what ends up happening is that this isn't really like two single bonds and two double bonds. If you actually look at this chemical, the strength of these bonds or the length of these bonds is kind of like somewhere between a single and a double bond. And what happens is when you have resonance like that, these bonds, they're all very, very stable. So that you release a lot of energy to form something with resonance. So this is very, very, very energy like exothermic when you form this phosphate ion. You don't get this. The electrons are kind of locked in place when they're in this larger thing. Like the double bonds can't be moving around quite so freely. But phosphate is it's a weak acid, but it's a pretty decent acid. So you'll see this ion fairly common. And so you get a lot of stability from that ion, which causes that to be very, very favorable to form. It's the same reason that you see like carboxylic or carbonate and carbonic acid, why that's a pretty good acid. You get this resonance structure that is very, very stable. And so what ends up happening is that you're not like just changing the bond energy of this one phosphate bond. No, you've changed the energy not just of this one, but of this one, and that one. All of them end up being a more stable bond. They all end up releasing more energy. So you can talk about like the average phosphate oxygen bonds energy, but in reality, these chemicals, they're not just the average values. They change slightly as the chemical changes. So there's something going on with resonance there that helps explain um, why this is so much lower. Like that phosphate, the energy released when you form an inorganic phosphate is significant because of that resonance. So that's one aspect of this. Then there's also the electrostatic repulsion. You can see like this is the ATP molecule that's just been separated. So you've got like the adenosine, you've got two phosphates and your third phosphate there. And I've shown the electrons, and I've got these little squigglies just showing how close they are. You can see that all of these electrons, like these electrons and those electrons, they're pretty close to each other in our drawn molecule. So they are crowded. These electrons, they don't want to be near each other. They would be more stable if they're further away. Like you can think about the two negative charges. If you have two negative charges, they repel each other. And so these electrons are trying to repel each other. So if you were to break the bond, suddenly these electrons, they have more space. Suddenly these electrons, they have more space. And so you're easing that crowding, or that what we call electrostatic, the electrons, that repulsion in the molecule. So when you break up the molecule, all of these phosphate oxygen bonds, all of those bonds end up becoming more stable. They end up like shrinking in size because they're a stronger bond, and the whole thing ends up being more stable. So we're not just, in that case, we're not like in, like, yes, there's an increase in energy because you broke this one thing, but there's a decrease in energy across all these different bonds. They all become slightly more negative than what they were because there's more energy being released, because it's more stable due to there not being as much crowding as there was previously, um, before that got broke. Because you can imagine before it got broke, there's this oxygen's close to these oxygens, electrons, and everything. And the double bonds too, they take up a good amount of space too. So it's pretty crowded in there with that electrostatic repulsion. Um, so it makes for more stable molecules if we can get rid of that crowding. There's one other kind of weird aspect to this. Now, if we look at ATP and ADP and all this other stuff, when we're measuring their standard reduction potentials, I got a whole video on this, but the standard potential, that's assuming that this is a 1 molar concentration. So these things, it is an exothermic reaction given that 1 molar assumption. So it does give off energy in standard conditions, but we actually have really weird conditions in our bodies where it's much, much smaller than 1 molar. It's actually measured in like millimolars. So the concentrations are very, very small. And because the concentrations are small, that actually changes the voltage and actually makes it even more spontaneous. So like this reaction is, it's pretty spontaneous going forward. Like if you looked at its K value, it's pretty big. Like it's releasing energy, so it's going to be spontaneous going forward. But the amount of energy that's released is used to going from like 1 molar concentrations. When we're at like Q nature, we've got really small numbers. And so the Q nature ends up being even smaller than the Q standard. And so it's got even further to go. So there's even more energy that's being released. And so the standard numbers actually become even slightly more negative due to the fact that this Q value is small, um, and making it therefore more negative, right? So there's some aspects of what's going on with the concentration here. Um, being different than the standard conditions that we do in a laboratory, just defined by how we like to define like voltages and K equilibrium and Q and everything. But it really, in my mind, it has much more to do with this resonance effect. I think the resonance is probably the most critical element of what's going on here. But the electrostatic repulsions is also relevant. Um, and also keep in mind that we're forming things like chemicals that are more stable due to all these bonds having better interactions where they're going, essentially, or having a better distribution of electrons and protons. Okay. Okay, so let's look at some example problems looking at like the bond energies and the energy of the reaction. Like if you have a reaction like this, it's just important to remember that breaking bonds, that needs energy, forming bonds releases energy. I always, whenever I do one of these problems, I just write out like the positive and negative and what that means, you know, so that it just helps me keep track of what's what. Um, while I'm doing the problem, right? So I can just keep track of this and I can think of like my two magnets, right? I've got these two things and I've got to separate them. That's going to take energy. And then I've got like my plus and minus, plus and minus. And so these things, when they fall towards each other, that's going to release energy. So just keep that in mind and you should be able to kind of think through this. And what I like to do is I don't really use like so much a formula. Is I know that these values, I know what the values are, and I kind of work with like my final minus initial. That's my in general strategy with these guys. And I'll tell you why. They usually will give you these values as just like positive numbers, right? When you're looking at the energy of these bonds, which is weird because I would expect them to be given as negatives. Because as we talked previously, when when you form a bond, it's releasing that much energy. So this is the energy that's released when that bond is formed, right? And so if we're thinking about the energy in the bond, you would think about representing that as a negative to really show that that energy is leaving the system when that bond is formed. That's how I like to think about these problems. I just always think about that negative as the energy leaving the system, and that helps me a whole lot. But then it messes you up with one of the equations that you might see with these. So if I think about this problem, I have two of these bonds, and these are kilojoules per mole. So if you have a mole of these bonds, that's how much energy is in a mole of those bonds. So if we double up these number of bonds, we're doubling up the number of moles that we're looking at in the reaction. So we have to double up that energy released when it's formed. So this is how much energy is released when one of these bonds is formed. We have two of them, so we need to keep account of two of these. So we have two of them, the products, or subtracting the reactants. And you can see that this is the energy of one of my HH bonds right here, the energy of one of my fluorine-fluorine bonds right here. And I've kept the signs in there because this is that minus sign right here. I'll just kind of do a little bit of color coordination so you can kind of keep track of that. So that purple one's just showing like the final minus initial, and like you really have, if you think about it, a final down here and initial up there. So you're going down, right? So you went down 544 kilojoules per mole. You can think about this as like the bond energies of the reactants and the products, right? This is that difference, and this is that negative 1,130, and this is that negative 586. Now, the reason I like to do it this way is that they'll oftentimes give you this one formula where this guy right here, and it really throws people off because you do plug in the positive values for that formula, right? But then when you're thinking about this one, you kind of need to work with the negatives. So like if you're working with positive or negative values, kind of depends on how they've set up the problem. It's really nasty. But if you think about this, this is the bond energy is broken minus the bond energy is formed. And this the bond energies, this is like the negative of a negative, right? Because it's the energy is broken. That's negative of what should be formed, which, you know. So they've got like negative, negative, and then they've got the minus here. And so that's how they're keeping track of that. And you can think of this as like the negative, negative, and then just one minus there. So you have to be kind of careful with the formulas. Just kind of check intuitively with it. And if you're confused by what I mean, I'll show you more about that, being careful with the formulas on the next one, okay? Okay, so this is the AP problem from the 2019 test, number 2, part G. I've just kind of pulled the relevant information. This is given in the resource page with all the reactions. This one was not. This was actually something that I got from the key, and it was given as just like a formula that you should be able to plug into. But it's very strange. And honestly, I don't like how these things are given as positive values. So when I think of these things, I think of them as like negative values because that's the energy being released when each one of these things form. And so if we're thinking about the change in H of formation of the products, what this is basically saying is that like the change in H, this is the products minus reactants, like all of the products minus all of the reactants. And you can see right here that your products, you're going to have like one bromine bond, and that's going to also be with one of the chlorine bonds. So that's my products right here, right? And then minus my reactants. Maybe we could do that in a different color. Do that green. Okay. And then our reactants here was the BrCl. And we actually have 2 of those. So these are kilojoules per mole, like I said in the last problem. If we're doubling up the bonds, that's doubling up how many molecules we're working with, which doubles up the number of moles that we're talking about in the reaction. So if you have like 2 of these in the reaction, you're going to be releasing or requiring twice as much energy if you're breaking or forming that bond, right? So if we think about these numbers right here, we've got our our products right here. And so our first one is the bromine, and we know that that is negative 193, and that's going to be added to a chlorine bond, which is negative 243. Okay, so that's our products, and then we're also going to subtract, and we're going to have our 2 times the BrCl, which is, I think this is our variable that we're trying to solve for in this problem. They haven't given us this one, but we do know the amount of energy and the difference between the 2 sides. So we can say that the energy change between these 2 sides is a positive 1.6 kilojoules per mole. It's important that this is a positive number, right? Showing that it's not spontaneously going forward. This is like energy is needing to enter the system. So in other words, if energy is having to enter the system, the products are higher energy than the reactants. They're less stable than the reactants. So you can think about this as our little like graph that we've been doing. You know that the products and the reactants, like it's going up 1.6. And what we're basically saying is like, oh, I'm plugging in these numbers for that right here. And I need to know it 2 times whatever this is, and I should be able to solve for that if I know the difference between the two. So if we go ahead and plug this in, let's see, we've got the 93 and 243. That's a negative 436. And then minus that 2x is equal to 1.6. And if you know your algebra, you should be able to see that how we need, and then subtract the 246 from both sides, and that should allow us to find things. I just want to, just highlight that this is that. This is that as well. And if we do that, that should get us a fair amount closer to our final answer. So 436 plus 1.6. We get that. And that is going to be equal to the, what's that, negative 2x. And that's equal to, what did we say this was? 437.6. And then we can divide both sides by 2. And we should get the amount of energy in one of these bonds. So if we do that, 436, divide that by 2, and we get 218.8. And I think we can round this. This is because it's an AP test question. I think that they're looking at this, and it looks like we had 2 sig figs. So you'd need to round this to 2 sig figs. I think that'd be like 220 kilojoules per mole, right? And so we can see that this is also, it should be a negative, right? Because this is the, like how these were negative numbers, this should also be a negative because it's a bond energy of how much is being released. And when that one bond is formed, you would expect that to be negative, seeing how we wrote those as negatives. So I made a small error with the sig figs. If you look here, there's actually supposed to be 3 significant figures, because it's not really about the number of significant figures, it's more about the place value, because we're adding and subtracting numbers here, and these were accurate to the ones place, and so this needs to be accurate to the ones place as well. So just a small error. So that's how I would think through these problems, and it really does match up with like more like these energy bar graphs, and you can think about this being the products being at, what's this, negative 436, and then the reactance was that 2 times that number is 237 point 437.6, right? So it was down here, then it went up there. It has increased in its value, but these are 2 fairly negative numbers. So that's how I like to think about it. Now you can use this one formula to solve these problems, but I tend to not like it because it's kind of conceptually weird. Now, the main reason I don't like this formula is that they're saying this is the bond energy is broken and bond energy is formed. And so when I think of broken and formed, I think of like the positive and negative signs that are associated with them, right? I'm just reminded of that. And so I think like, oh, like formed, that's going to be releasing energy. So these should be negative values. And broken is going to be positive because that's the sign that you get with those. That's not really how this works in this equation. No, these are all positives. All positive bond values. So if you actually were to plug these in, it ends up looking kind of like this. And you can see that this, you've changed the signs and you've also flipped which one's in the front and the back. It's kind of how that relates to what I had done just a second ago. But this is that other formula where you're actually using positive values. So it's weird because in one formula you have to use the bond energies given as positive values and just kind of plug them in. Or the other one, you have to think about the energies and kind of conceptually see and keep track of what's going on and the amount of energy and bonds of the two sides. I like this first part more. This one is technically easier because you just plug in the positive values, but you need to be able to conceptually check your math, right? And that's kind of harder to do with this, where they aren't really conceptually keeping track of that. So this is another formula. In this case, all the bond values are positive. I like to do the sum of my different values and keep track of them as negatives. Just helps me connect that to the exothermic, endothermic in the end, and it helps you relate the bond energies and what they really are as negative values being stable and lower, right? Because I don't want to give off the impression that there's like higher energy or unstable things having a large bond energy, right? Because large bond energy is very negative, so that should be very stable. So it's important to keep that positive negative in mind when you're doing these kinds of calculations, and just being aware of how the formula that you're using, what those values should be, plugging it in and kind of double checking with what you know. And if you don't know, just plug in some values, plug in like a bond strength of like 10 and 1, right? Like you're like, okay, let's say that like the product's got to be -10, the reactants are got to be -1, and I expect it to be exothermic. And you can just kind of plug that in and see if that relates in the equation how you'd expect. Okay. All right. I think that's everything for me. Thanks for joining me. This has been Andrew McLaren. Thank you for McLearning with me. I've got a few more offers that I'd like to let you know about. And remember, like and subscribe. For each video on YouTube, I am making an interactive version using HP5. These will be for sale on Podia. And if you click on the link in the video, you should be able to go directly to that product. I also have 2 demos I'm going to be linking so you can kind of see what these products look like. So I would recommend checking out those demos. I also offer one-on-one remote tutoring through Wyzant. Please use the links that I have linked below. That way I can get 100% of the hourly rate as opposed to 75. Each video also has a link for my Patreon, and you can join at the $3 level to get some resources I use for tutoring or to support the channel. And I also have a $5 raffle level, which you could either get some free online tutoring or 5 interactive lessons for free. You choose which ones. And then I also have my Teachers Pay Teachers, which has some old lessons that I made from when I used to be a teacher. I may be adding to that. Thank you for spending your time with me. I hope that you learned something.